Today we're going to talk about light, color, and how light and color are related to the structure of atoms. And then we're going to use that to explain how the first model of the atom developed that took into account where the electrons might possibly be. When we see white light, we're really not seeing a color of light. We're seeing many colors of light, all the colors of light possibly, blended together as one. Our eyes kind of add the light up. They can't separate the colors out. And so we see a kind of a sum. When we see colored light, it could be because of three different possible reasons. One of them could be that a prism, or a diffraction grating, which functions like a prism, separates the colors. This picture here shows a familiar, almost an icon of light. When white light comes through a prism, it separates out into its different colors. Our eyes can't do that, but we have tools that allow us to do that. So if we're seeing colored light, that could be one reason that we're seeing colored light. Another reason is it's possible that the light we're looking at only is one color. If you pass green light, for example, through a prism, you just get green light out. It doesn't separate into any other colors, so that could be another possibility. This model is a way of visualizing that. This guy's looking at three different lamps. Right now they're all turned off. I'm going to turn on the red lamp, and you can see red light hitting his eyes, and up in his little brain bulb here, what we're seeing is his eyes interpret red light. Now I'm going to add some green light, and you can see that the color changes. His brain automatically mixes those colors and he gets a kind of a yellowish color. I'm going to add blue light to the mix, and now with all three of these colors mixed together, we see that this person is visualizing this as white light. It's the sum of all the light. If I turn off the green and we see only red and blue, he's visualizing violet. If I have the blue and the green on and turn off the red, he gets this cyan color. It's kind of a lightish blue color. So the sum of all the light looks white. Take away all the colors but one, like green, for example, and all the person sees is green. So that's one reason that you might see colored light. It's because there's only that color of light available. Another reason, of course, might be because a prism has separated light into its colors. Here's another possibility. This person has got a light that's giving off white light, and he's looking at it, and you can see up in his brain he's interpreting that as white light because his eyes are summing together all the colors. Now, I'm going to place a filter between the bulb and his eyes, and I'm going to make that filter blue. When I turn the filter on, he sees blue color. And what's happening is this filter is taking out other colors. Primarily, this is taking out yellow light, because yellow is what we call the complementary color. If I change the filter color to red, he sees red. So even though there's white light there, it's being not separated by a prism, but all the other colors are being absorbed by some dye in the filter, leaving only an unbalanced spectrum that gives him a certain color. So what happens in those instances can be interpreted using the artist's complementary color wheel. Whenever one color is removed from the spectrum, we see the complementary color, which is 180 degrees away from it on this color wheel. So, for example, if I were to take out this color of magenta, if I were to remove that, 180 degrees from that, we would see green is, or that color of green would be the color that we would observe. So, for example, a blue shirt looks blue because there's something in the dye of that shirt that removes yellow light. Here's another example. Cherry Kool-Aid has a dye in it. That dye makes the Kool-Aid look red. Here's why it makes it look red. It takes out some color of light that is bluish green, and that gives it that red color. So the complementary color being removed from the spectrum also makes it look colored. So those are three reasons that light might look colored to us. It turns out that when gas atoms are put into a tube, sealed up, and then given electrical energy, the atoms do two things. First of all, they enter an excited state. They take the electrical energy that they've absorbed, and somehow they become excited. Now, excited for atoms doesn't mean that they're like anxious for something to happen or looking forward to something. It just means they have more energy than they normally would. But that doesn't last for very long, and eventually the atoms return back to normal, and then when they do, the electrical energy that they absorbed, They give it back, but they don't give it back as electricity. They give it back as light. And that light is usually colored light. An example is neon light. We've seen neon lights all of our lives because they're used in advertising signs like this one here, and it gives off a pink light. Another example is yellow sodium light. Much of the time when we look at street lamps nowadays, we see yellowish orange kind of light. That's because we have a sodium vapor light. So this light bulb here is glowing yellow, not white, and that's going to affect how things look. Only one color of light is coming out of there. In this visualization, what you're looking at here is what we might be able to see if we could see atoms inside of a neon light. Every one of these atoms here represents a neon atom, and the number that's on them is what energy state they're in. Most of them are in state number 1. A few of these are in state number 2. I'm not sure why the visualization looks like that. Now watch what happens when I fire an electron in here, and I'm going to run this electron in here in slow motion. Here comes one single electron being emitted. It smacks into an atom and it jumps up to level 9, and then it comes back down to level 1. Now as it does that, look what's happening. Photons of light energy come out, and they can also hit other atoms, and they can emit other photons of light. But we're only getting certain colors of light. In fact, we only saw a sort of a purple color come out of there. What happens if I start to stream a lot of electrons into my atoms? You can see that I'm jumping into different energy states, 10s, 3s, 7s, 6s, 2s, 4s, 9s, and when it jumps to each different state and jumps back down, it's emitting different photons of light energy. And so now I'm seeing not just that purple color, but I'm seeing a large number of colors. I'm going to open a tool called the spectrometer here. This is a simulation of a real-life tool that sort of collects photons and makes a graph, almost like a bar graph, of which colors are showing up, which kinds of light are being produced. And I'm going to turn it into high-speed motion so we can fill our bar graph up fast. What you'll notice as this bar graph begins to fill up is that there are some colors that just aren't there. The neon in this tube is only producing predominantly yellowy, orangey, red kind of light. It's also producing a big ultraviolet component, but we couldn't see that. So here's why neon light looks pink. It's only producing colors that our eyes mix together to make a pinkish color. The colors that would make it look white, that would balance this reddish kind of spectrum, just aren't there. Let's look at another one. I'm going to change the atoms to sodium atoms and build my spectrum. What's happening is, even though I'm discharging the same number of electrons per second, it's the same electrical discharge, I'm not getting the same spectrum. There's something about sodium atoms that only give us these two visible colors. One is kind of orange and one's kind of yellow. And that's why a sodium vapor lamp looks yellow. There are some other bars here, but they're infrared and ultraviolet, and so we wouldn't see those. So just like we saw with our spectrometer, you can take the light that comes from a neon light, you can take the light that comes from a sodium vapor street lamp, and you can pass them through a prism or a diffraction grating, and you'll get a spectrum, a rainbow, but it's a discontinuous rainbow. It's a rainbow that's missing some colors. Here's the neon rainbow that you'd get. Predominantly, it's these pinkish and yellowish colors. So we see pink. Only two visible lines in the sodium spectrum, right there. And so you see that as a yellow light. Let's look at some other line spectra. Here's what helium looks like. In this spectrum, we see a sort of a background rainbow, but only the heavy lines here, the bright ones, are the ones that you'd actually see if you had helium in a tube like a neon light. Here's nitrogen, a discontinuous spectrum again. Here's mercury. Mercury vapor lamps are the old style street lamps that look more whitish, but they're kind of a bluish white light. If you spend any time over at the skate park, you have observed a mercury vapor street lamp, and it's not that yellowish tinted light that you see in other places around town. Well, the colors that are here in these discontinuous spectra, this kind of a spectrum is called a line spectrum, and every element has its own. It's a sort of a fingerprint almost of the atom. People became really interested in this one. This is hydrogen. And the reason that they were interested in it is because they were looking for the connection between light and how atoms behave. And they thought it would be easiest to make that connection if they were looking at the simplest of all possible atoms, which would be hydrogen, because it has only one proton and only one electron. So they thought, we'll figure out what's going on with hydrogen, and if we can do that, well, then we should be able to extrapolate to more complicated atoms after that. So they see only these 5 lines. You might only see 4 if you looked at a real spectrum. This one down here in the end is really close to ultraviolet, and some people can't see it. Our eyes are all slightly different. Well, they asked themselves this: do those 5 lines correspond to 5 different places where the electron is in the atom? Is that what's going on here? And that's what most people thought. And it turned out that the answer was no. That really wasn't what was going on. A better answer was related to 2 different states of energy. So looking at this graph, we see that this, with a state 2 energy, will have more energy stored in it. So this is an excited atom. In state 1, there would be less energy stored in it. The difference between state 1 and state 2, that's the amount of energy that it takes to give off a photon of a particular color of light. Or, if light is absorbed by the atom, that will be just enough energy to jump it from state 1 up to state 2. A small difference in state, if state 2 and state 1 are very close together, you're going to get red light because it doesn't have as much energy. A big difference in energy, if state 2 and state 1 have a very large gap, you're going to get bluer light. And then other colors are going to come from gaps that are not on the extremes. So that color right there, that near ultraviolet or very violet color, that comes from a pretty big energy jump. This red one here comes from a much smaller energy jump in the atom. So a small energy difference results in a lower energy red light. A big energy difference results in a higher energy blue light. Now you only see certain colors. For hydrogen, in the visible spectrum, you only see 5 colors. So that means there's a limited number of jumps that are possible in the structure of this energy in the atom. Here's how you could possibly explain this. Let's pretend that this chart represents hydrogen's possible energy states. If the electron can only exist in these 4 states, then that means that there are a limited number of transitions that the electrons can undergo. For example, one of them would be a state 2 to state 1 drop. That's a fairly small energy gap, so you see some red light. A state 3 to state 1 drop is a little bit more energy, and so you see light that's a little bit closer to the greenish-blue area. The drop from state 4 all the way down to state 1 is a pretty large line, and so that might be that violet color because it's a big energy gap. You could have a drop from state 4 down to state 2. That wouldn't be quite as violet, to be a little bit more towards the indigo or blue, but it's bigger than the state 2 to state 1 drop. And the state 4 to state 3 drop gives something that's closer to blue-green than the 4 to 2 or 4 to 1. So here we see 5 possible lines that you could get from this structure, and that might match the 5 lines that are in the spectrum. Now we could actually propose that there would be another line. It's possible that we could have a drop from state 3 to state 2. We haven't seen that gap here. But that's a pretty small energy drop, and it's possible that that might be not visible to us. That would be in the infrared part of the spectrum that we can't see. So that's a possible explanation. The idea here is that the electron can't exist in any state except for these allowable states. So these are sort of like rungs of a ladder. You can stand on rung number 1 and rung number 2 and rung number 3, but you can't stand on rung 2.5. That's not possible because there's nothing to stand on. That's sort of the idea that was developing here, that the electrons could only possibly be in these states. This idea is what we call the quantum theory, or it's part of what we call the quantum theory. And the quantum theory says that all changes are discontinuous or discrete changes, that there are these little jumps, and that things aren't smooth and continuous like we see them in large-scale life. The first person who developed an atomic model based on this quantum idea was a guy named Niels Bohr. Here you see a picture of Niels Bohr. That's Niels Bohr chilling with another famous scientist that you probably recognize there. Here's Niels Bohr's idea. He said that the electron is orbiting the nucleus, kind of like a planet orbits the sun, spinning around in these orbits. If it's in a low orbit, it has less energy. If it's in a higher orbit, if it can jump up to a higher orbit because it's been given energy, well, then it's going to have more energy in that orbit. It's going in a bigger path, so it would have more energy. And then he says if it drops back down to that lower orbit, it will give off some light energy. And he said since there are a number of possible drops, it will give off a number of different lines, a number of different colors. So a small drop gives some red light. Drop from orbit 3 to orbit 1 would give that teal colored light. Bigger drop would give even bluer light. And all these different orbit drops would result in different colors of light. So when the electron's in a small orbit, it has less energy. In a large orbit, it has more energy. And the drops from orbit to orbit give off the blue and red colors of light. Small drop, red light. Big drop, blue light. Since the electron can only exist in certain orbits and not between them, well, that means that you would get a line spectrum. You wouldn't get a continuous rainbow. Well, Bohr knew stuff. Like one of the things that he knew was the mass of a proton. He knew how much a proton weighed. He also knew the mass of the electron. This stuff was well known at Bohr's time. And he knew the equations that would calculate how much energy an electron and a proton would have if they were in this planet orbit system. So here's your proton, the electron circulating around that proton. He knows the charge, and he knows the equation that shows how much attraction there's going to be. He can equate that to the sort of equations that were used to calculate the Earth's orbit around the Sun or the Moon's orbit around the Earth. All of these were well-known equations. Every physicist knew them. So Bohr applied them to this little system, and it turns out that when he calculated the amount of energy that would be in every orbit and then subtracted the differences between the orbits, he could predict the line spectrum that his model atom should produce. He could predict what colors should you see if his model was right. And it turns out that he was right. Every color that you produce in his calculations is exactly a color that you see in the hydrogen line spectrum. And you don't see any other colors except the ones that his model would predict. Correctly predicted the line spectrum of the hydrogen atom. So his theory became widely accepted at the time, and people were fairly sure that we now knew what the atom was like. Turns out that Bohr's atom had some problems, and the model had to be refined. But it was a real great triumph at the time, and it was our first look at how atoms might behave that explained what we saw from light. Next time we'll look at what the problems were and the refinements that led to the current model that we have for an atom.